In this lesson, we will determine zeros of a polynomial function. Testing potential zeros. If f be a polynomial function and c be a real zero of f, then the point c, 0, where the graph touches or crosses the x-axis is called the x-intercept, and the real number of zeros are the x-intercepts of the graph of the function. So here we have a function, and we're looking for the point on this graph to where it touches or crosses the x-axis. And we can see here that those 2 points are at 3, 0 and at 7, 0. So where they touch at 3 and 7, that is called the zeros or the x-intercepts of a function when given a graph. Okay, so if you are not given a graph where you can visually see the zeros of a polynomial function, then you're going to have to use some other method. Now, the remainder theorem is one of the quickest method for finding the zeros of a function if you're not given a graph. So a zero of a polynomial function, f, is a number, k, such that f of k equals 0. So remember the remainder theorem, that the divisor, if you were to plug it in, your input, that what you would get out is your remainder. So if your remainder that you get out, if is 0, then that is proof that whatever you plugged in, that number is a zero of that function. Okay, so you will use synthetic division, and if the remainder is 0, then that number, that divisor number, it is a zero of that function. So let's do an example to see exactly what we mean by all this. So here we're given a function, f of x equals this polynomial function that's been given, and k is 1. So we want to find out if k, in this case k is 1, so we want to find out if 1 is a zero of that function. Well, the only way you're going to find out is, 1, you can evaluate it for that function. In other words, everywhere you see an x, you can plug in a 1 and see what you get out. And if you get a 0 out, then that's proof that yes, 1 is a zero of that polynomial function. If that way is quicker for you, you can also use that option as well. The other option that I find very quick is to use synthetic division. So in synthetic division, recall, you're going to have the divisor of k, which is 1 in this case. It's going to be on the outside, and then take the coefficients of your polynomial. It's going to go under the symbol. Now, when we do this, if we get a 0 for remainder, then that is proof that 1 is a zero of the polynomial function given. So let's go ahead and begin our synthetic division process. We're going to bring down the 1, multiply it with 1 to get 1. Bring down a -3, multiply that with 1 to get -3. Bring down a 6, multiply that with 1 to get 6. Bring down 0, we have a remainder of 0, so therefore there is your proof that 1 is a zero of the given function, because f of 1 equals 0. And there you have it, testing potential zeros using the remainder theorem. Let's do another problem, and we want to test the function to see if negative 4 is a zero of the given polynomial function. So recall, you can either do two methods. You can either plug negative 4 in, remove all the x's, replace them with negative 4, and whatever output you get, if your output is a 0, then that is proof that negative 4 is a 0 of that polynomial function. However, if you plug it in and you do not get a 0 out, then that means that negative 4 is not a 0 of that polynomial function. The other method which we're going to use is we're going to use the synthetic division, which is also a very quick method to use. And we're going to use the divisor of negative 4 and divide it with our given polynomial function. Recall, we only need the coefficients, and we're going to begin that process. Now, once we do this, if we get a 0 out for a remainder, then that is proof that negative 4 is a 0. However, when we finish this at the end, if we do not get a 0 and we get some number, then that means that negative 4 is not a potential 0. So I'm going to ask you to stop the tape for a moment and stop the video for a moment. I want you to do the problem, and I want you to tell me whether negative 4 is or whether negative 4 is not a 0 of this polynomial function. Okay, so let's see how you did. Let's begin the synthetic division process. We're going to bring down a 1, multiply that with negative 4 to get negative 4. Bring down a negative 4, multiply that with negative 4 to get 16. Bring down a 17, multiply that with negative 4 to get negative 68. Combine these and bring down negative 71, multiply that with negative 4 to get positive 284. Bring down 285. We did not get a 0 at the end. We do not have a remainder of 0. So that means that negative 4 is not a 0 of this given polynomial function. And there you have it, testing potential zeros using the remainder theorem and synthetic division. So we're going to do one more. Now this one is a little bit more complex than the others, but I want to touch on this one because on your homework you may find one of the problems similar. So this is how you would work it. So you're going to have to go back and recall your knowledge about complex numbers when you're subtracting, and multiplying complex numbers. Complex numbers means real and imaginary numbers. So let's begin. We want to know if 1 plus 2i is a 0 of the given polynomial function. So that's going to be our divisor, which goes on the outside. So I'm going to begin the process of this one, and I'm going to go through all the division, and on the screen to the right I'm going to show how they were multiplied in case you want to know how they were multiplied. But again, you're going to have to recall your knowledge about how to add, subtract, and multiply complex numbers, which should have been covered in the section or the course before this one. All right, so we're going to begin by bring down the 1, multiply that with 1 plus 2i. 1 times any number is going to be that same number. So we're going to bring that over. You can only combine the real with the real. You can't combine the real with the imaginary. So combining the real with the real and bringing the imaginary down is going to leave us with negative 1 plus 2i. Now we're going to multiply that with 1 plus 2i, which is nothing more than FOIL, first, outer, inner, last, and that's going to give us -5. Combine these two together. I'm going to bring down -1, multiply that with my outer divisor to give me -1 minus 2i. Combining the real with the real, I'm going to bring down 1 minus 2i, multiply that with the outer divisor, and that is nothing more than conjugates, 1 plus 2i, 1 minus 2i. You can multiply first and last, or you can just do FOIL. Either way, it's going to give you a result of 5. Combine your last, and you have a 0. So now that is proof, the fact that you have a 0 as a remainder, it is proof that 1 plus 2i is a 0 of this function. But not only is 1 plus 2i a 0 of a function, of this function, because we have a remainder of 0, but by the conjugate theorem, if 1 plus 2i is a 0 of this polynomial function, then 1 minus 2i must also be a 0 of this polynomial function. Now, the fact that it is a 0, it is not a real number 0 solution. Okay, this is a complex number. So if you were to graph this, it would not touch the x-axis because 1 plus 2i or 1 minus 2i, those are not considered a real number solution. It is a complex solution. So the bottom line is, if you wanted to know whether 1 plus 2i is a 0, yes, it is a 0. It's just not a real number 0. It is a complex number 0. But yes, it is a 0 of the polynomial function. Okay, that's it for this lesson. Thank you for watching MVP Tutorials by your instructor, Dr. Speights. I hope you'll join me in the next lesson. Please feel free to like, share, and subscribe. Goodbye for now.